Hello, everyone. Nice to see you again for this new installment of the Gossip News Flashes. We do that weekly. Um, so we're gonna wait just a minute for people to arrive. Okay, then let's start slowly. So hello and welcome to this new Gossip News Flash. We have quite a few news this week since last week. First of all, I'm gonna run you through the changes in the Gossip implementation. What's new? So from January 16 to January 13, we have improved security and privacy. Typically, there's now the screenshot protection by default, so you cannot take screenshots of the app. That's about protection of the app itself for privacy. You can toggle it in the debug settings for now. Uh, the Somebody from the community also brought up that some of our fonts depended on Google Fonts. That's been removed, so there's no more external dependencies. Thank you for this. Um, the user interface and experience were improved. We have improved iOS keyboard management, discussion filtering and sorting. Now you can search more efficiently, sort, filter. We have improved also the communication side, so the announcement and messages, pagination. There's an automatic session, like a refreshment of broken sessions, etc., etc. So this should be smoother. Um, we also have integrated the Massa name service (MNS) for the people who want to have like their MNS, their name used as a tag for others to be able to find them. It's optional, of course, but they can declare a name, and from there, others can find them with that name. So if you search somebody by their nickname. Currently, it's not possible, and now it's possible. We also improved quite a few of the developer and infrastructure side things, and we are working on also on a few big new things. One of them is, of course, debugging a bit the system before we release all these additions, because there's still a few bugs. We need to solve them before we release. Expect to release very soon. We're gonna tell you, but for now, it's still the old version that you're gonna download. If you want to follow what's happening, you can also follow our GitHub. Everything is open. You can look at it. And uh, from the standpoint of what's currently ongoing, we are preparing the work for the decentralized backend. So that's kind of a big work to be able to reach areas with high internet censorship. We are also working on plausible deniability of sessions so that you can have multiple sessions hidden. I will tell you more about this on the next call because we'll have made progress. But for now, we have made a specification that's really nice. You can find it in the discussions of the Gossip repository on GitHub. Uh, anyway, the idea is that if somebody steals your phone, they cannot find your sessions. They don't know if they decrypt one session, they don't know if there's other sessions. So that's the idea. What's interesting here is also what we have been working on in the vein of hiding, uh, basically allowing Gossip to access areas that are under high censorship. And one first element we started to tackle that's not been tackled much by others, at least not in that way, was being able to circumvent whitelisting. So what's whitelisting? In more and more countries around the world, uh, under certain events or maybe even permanently sometimes, the government only allows computers to connect to an authorized list of IP addresses. This means that nothing like Session or SimpleX or Telegram or Signal, none of those will work in that context because their IP addresses are not on the allow list. They're not allowed. It's worse than a blacklist system. blacklist system, the government just forbids access to some IP addresses. Here, it only allows access to some IP addresses. So this is a phenomenon that's been propagating around the world, and we are trying to see how we can circumvent it. Usually, the governments that do that, they don't completely shut down the internet because they know that users will find ways to communicate, etc., etc. They prefer to provide their own solutions for communication to the users, which are typically different kinds of chat apps that allow users to chat, exchange messaging, exchange voice, do video calls. And these services are whitelisted because they're controlled by the government. And we have had quite a few activists tell us that this was a growing issue and that we should try to tackle it. And we thought, what would be the best way to bring data through such systems that are government controlled, that allow for chatting, but under the nose of the government? Well, one approach that we imagined, I'm going to present. So let's show the slides. Okay. I hope you can see my slides. That's how we imagine doing, basically hiding data through a video call in a way that is not like others do, but the video call still looks like a normal video call. So even if you decode the video call, if you see the picture, it still looks like the original video call. And it's a live video call, and we're gonna try to hide data inside. So it's gonna be a live stream of video, of images, and a live stream of data. Both need to be fused. They need to resist compression, because remember, when video is sent on the line, it's compressed. It needs to go through the internet, get decompressed on the other side, and we should be able to retrieve, on the one hand, the original video. It should be seamless, and also the encoded hidden data. That way we can use actually these government services as channels to channel data in a hidden fashion and seamlessly, so it looks like a normal video call. And that's tricky. That's hard. So here is the general schematic of how it works. The idea is that we have here on the left, the original, top left, the original stream, the video stream. We need to create some kind of encoder that takes the original video, that takes also some analog data stream, that adds it to somehow that combines it with the image in a seamless way. This encoder has some goals. It needs to work. It needs to be very lightweight, so it must run directly on the phone, live, on a reasonable phone, like something fancy, that encodes this data live. The encoded stream should look reasonably similar to the original stream, so it should not degrade the picture too much. Then there's going to be this compression on the line, and this encoding needs to survive that compression, because the compressed stream is sent through the internet to the receiver, the other phone, and that other phone needs to be able to run a decoder on the received image and be able to retrieve the original data that's been sent. And this is very tricky to implement, because this stream needs to look like a normal stream. The video, when agents look at it, it should look like normal video. And this data should be hidden inside. And despite compression, we should be able to retrieve as much of it here and perform some error correction, whatever, to be able to retrieve as much of it as possible, so that we can channel data live through these video calls. And the way we did it is that we created small neural networks, an encoder and a decoder. It's the pink ones here. And that's how we train them. We design them ourselves, and we train them ourselves. So we have at Masa Labs, we have hardware that allows us to train on site, because usually no other training rig kind of allows this kind of applications. Hiding data into video streams is considered out of bounds even for ChatGPT. So here we train our own models from scratch at Masa Labs on our own hardware. So we take the original stream, we pass it through the encoder, we take some random data, we pass it through the encoder, we obtain the encoded stream. Here, the first criterion we need to optimize for is to ensure that there is no strong visible difference between the original stream and the encoded stream, despite the encoding, so that the data is not like completely scrambled and we only see some kind of colors everywhere and we don't even see the original stream. Then it's obvious that we're hiding data there. So we use something called perception difference. So for those who know, it's a differentiable way to measure the perceived difference between two images. We use PIPS here as a first error. So this needs to be minimized. This error needs to be minimized between the original stream and the encoded stream. Then we apply stream compression to obtain the compressed stream. This is non-differentiable. And this compressed stream is fed to another neural network, which is the decoder. And for those who know a bit, we cannot differentiate through stream compression here. So we do pass-through here that simulates basically the gradient flows that way for those who understand neural networks. And then it enters the decoder. The decoder also needs to run on the phone, be lightweight, run real time, and then it's going to output the analog data channel as the output. And then we minimize the difference between the original encoded analog data channel and what we obtained from the decoder. So we have worked a bit on this, and I can show you actually a live demo because we have trained the first iteration of this system. So I'm just gonna change the tab I'm sharing. Give me a sec. Okay, I hope you see my screen. So on this screen, it's live, it's me. It's running inside an ONNX neural network system inside a web page. And actually, I can also run it on my phone. I'm gonna prepare it on my phone as well. Yes, here we go. So here I can choose the compression quality. Of course, here I put it to the minimum. So it's maximum compression. There's a lot of artifacts. We lost a lot of quality in the image. And our goal is to see in the worst case scenario how much data we can get through. So what happens is that, remember, there's a neural network that takes this original image, hides some random data inside of it. We hide 256 analog channels inside the data. We obtain the encoded image, and this encoded image, originally, it looks a bit like this, like what you see here. So you see there's still a bit of artifacts. We're trying to reduce them. We're still training neural networks to reduce these low artifacts, the low flickers we see. But the goal is to survive very high compression rates. And as you can see, here we can see the signal-to-noise ratios through the whole pipeline. So from the original image, through the neural networks, the encoder, then the compression, then the decoder, and then we see the end data that's decoded. And so here it processes on my computer 21 frames per second. The mean error is very tiny. The signal is very strong. And here we can see all the 256 channels making almost zero error. So that's the correct matching rate. And if we reduce compression quality, of course, we lose signal to noise ratio. There's more noise due to compression. And here's the worst case scenario, 10% compression. So it doesn't get much worse. And we still have 6 decibels. And that's actually enough to get data through. So how do we encode the data? There's multiple ways. For example, when we are at high qualities, we have 256 analog channels, remember? What we do is that we have a first part, which is a payload, which are bytes. And the second part, which is a CRC. So it's integrity control for the data, because if something gets corrupted in the data over the flow, we need to detect it and to reject that piece of data. So here, for example, we achieve 100% CRC pass. So all the frames that go through perfectly. And here we are at about 50% compression quality. The payload is 14 bytes, and the CRC is 2 bytes. So the more CRC we put, the higher the detection rate is for bad frames, but less space we have for payload. Then what we do is that we take this payload and CRC, we concatenate them, and we obtain a series of bytes. These bytes, we're gonna split them into bits, and we're gonna split them into something called the PAM. How can I explain that? Let's say that every one of the channels is analog. So we could divide the values that this channel can take into either two values, two levels. So from 0 to 0.5, it's, let's say, a 0, and above it's a 1. That's 2 PAM. So that's the best way to resist to very high noise. But under reasonable noise, let's say quality 50%, we can go to PAM levels that are higher, let's say 4 PAM, and then we can increase the payload. We can increase the payload much higher. For example, we can achieve 30 byte payload and 2 byte CRC on 4 PAM while having 100% CRC pass rate and 2 times redundancy. So the whole data is copied twice among the bins here. And with this, we achieve about 700 bytes per second that are CRC verified after fact. So here's a perfect transmission, live transmission of data through this video. We can also, but if you look at it, if we increase compression rate, suddenly the CRC pass falls almost to zero, like 0 here. I think it's a bit higher on certain levels, like maybe if we go for, basically there's a compression level after which we don't get much data through anymore with this level of encoding. That's why if we want to channel through channels that have much lower quality, let's say we have this low internet throughputs, very high compression of the image, we need to get back to true PAM. And at true PAM, the optimum that we have found is 14 bytes of data frames, 2 bytes of CRC, twice redundancy. And there we can channel live all these frames despite the horrible video quality. So now we achieved 300 bytes per second. I'm running this exact same thing on my phone. Let me just adjust it the same way. And here on my phone, it's running live both the encoder and the decoder, and it achieves about right now about 50 bytes per second. That's because the phone is less strong than the computer would be. But 60 bytes per second on a normal phone, this is very good because it allows us to encode discussions live. For a test discussion, it's perfect. Of course, for video stream over video stream, it's another story. But for text, for small files, for some basic stuff, you see that even on the phone, surviving very high compression rates of the stream, we managed to encode quite a bit of data per second. And that's great because this is the first element. We're going to continue improving it, of course, but this is the very first element that allows us to, from there, build channels that survive whitelisting. So this is the first kind of whitelisting, the one that we hope has the highest possible throughput, which is video steganography. Our next steps would be to also look into audio and also in text. So what does it mean? Text steganography means sending messages that look normal. When you look at them, it looks like a normal conversation, but they channel data through. That's particularly useful, for example, in areas where a whitelisting is so strong that only SMS is allowed because the government uses it. In some areas in Africa, it happened recently. Only SMS was allowed. So having a way to channel hidden data through SMS in a way that doesn't make it look like hexadecimal code, which is obvious that you're hiding something, we can channel it in a smarter way. So that's our next steps. So I'm going to get back to our main screen. That's it for today. I'm going to have a quick at the chat. Yeah. That's it for today. If you have any questions, feel free to ask. So this was our demo of how we are building these new channels to communicate even in areas of high censorship. The goal is that when we build the backend in Gossip, from the point of view of the user in Gossip, Gossip should be smart enough when it's finished, when it's working, to automatically select the best channels possible, depending on the situation you are in. If you have a good internet connection, it's going to use the good internet connection and behave just like WhatsApp. If you have a bad internet connection, if you're in an area that's censored, it should be very easy, a turnkey thing that automatically channels it through different channels. We're imagining getting inspiration from the way BitChat is built for everything related to Bluetooth mesh. For areas with whitelisting, we want to create these kind of channels, typically being able to seamlessly have some volunteers call each other, create channels between people through video calls, through audio calls in areas that where only this is possible. And they would be channeling the data for the people who need to access the service and that are in these areas that are under strict control. And all this needs to be as discreet as possible. So this is where we are at. So this is one of the first building blocks. The goal is to build many of those and to have something that's really seamless in terms of backend for Gossip. I hope this. I see only one question here in the chat because I didn't open the chat before. Sorry, it doesn't register the previous one. So how will it be usable for Gossip? Well, exactly like I just said, it should be seamless, and people who are in censored area should be able to access Gossip. Okay, I hope this answers everybody's interrogations. If you have more questions, feel free to ask in our channels, in the Gossip socials. We're going to continue developing. Feel free to try the software. It's still at a very early stage. If you have any people who need any kind of censorship resistance, any kind of activists, anybody who needs these kind of things, tell us, especially if they require some functions that are absent from existing software. Our goal is to build this in a way that provides freedom of expression and speech to everybody around the world. So we don't differentiate. Just tell us what people need, what you would like to see. If you see bugs in the system, tell us. If you have ideas, let's talk. Everything is open source. If you want to contribute, feel free to play around with the code. Everything is on GitHub. It's linked on our website, usegossip.com. Yeah, and we're gonna see each other also next week. So I'll do another call next week to tell you all the news. And until then, thank you for your attention. And thank you, everyone. You're amazing. See you soon.